All right, in this video, we are going to move into section 1.5 that has a fancy name to it, but really it's not. It's kind of a nice little shortcut that we're going to learn here. So we're going to be doing Leibniz notation and then learn what the power and sum and difference rules are. Probably the scary word in this title is this one right here, but we're not going to sweat too much on it. It's just a fancy name for a way we can write derivatives that we talked about last time, and we'll go into that in just a second. All right, so let's go ahead and talk about it. So Leibniz notation. So when y is a function of x, we talked about last time that we can denote the derivative as f prime of x. We can also use this Leibniz notation, which is denoted as dy dx. So whenever you see this dy dx term and f prime of x that we covered in the last video mean the exact same thing. The only difference may be how you read it out loud. Whenever you have dy dx, do note that that means you're taking the derivative of y, which is your letter on top, with respect to the letter on the bottom, which is x. For the most part in this class, we will be doing dy dx as the only Leibniz notation. We will see some other notations later on in chapter 3 in the second half of this class, but for now, we're going to focus on dy dx. So that being said, what have we learned so far? These are our four notations that represent the derivative of a function. We saw f prime of x in the last video. We saw this limit definition in the last video. So we talked about how to find f prime of x by doing the limit as h approaches 0 of the difference quotient. We've now talked about that dy dx means the exact same thing. And then one other notation you might see us occasionally use is y prime. This is really just a shorthand notation to represent derivatives. I probably won't use it a whole lot, but there is one section upcoming that I'll use it a lot so I can keep everything kind of organized. All right, so now that we kind of covered Leibniz notation, let's move into the shortcuts. So I mentioned in the last video that when we learned the first way to do the derivative, that there would be a faster way to do this in the next video. Well, that is this. This is called the power rule. So the power rule is the backbone to all the derivative rules that we're going to be covering in the next 3 videos. So here's what it says. It says for any real number k, if you have a function written as y equals x raised to the k, then you can take the derivative of this by doing the following rule. The derivative of x to the k tells us that we can take our power of k and bring it to the front. So that's where this k in the front's coming from. You bring the x over, and then you need to subtract 1 from the original power. So let me say that again. When you do the power rule, you're going to bring your power to the front, and then you're going to leave the x alone, and you're going to subtract 1 from the power. Learning this rule will allow us to do derivatives 100 times faster and allow us to move into more application stuff throughout the rest of this semester. So, for example, here are 4 problems that we can take the derivative of using the power rule. So let's go over each one of these together. Example 1. What is the derivative of y equals x cubed? Well, if you want to find the derivative, and just to show you, I'll use the notation y prime because the y's are here. Power rule says you take the 3 and bring it to the front, leave the x alone, and then subtract 1 from the power, which makes this a 2. And that's it. This is a lot faster than having to do the difference quotient over and over again. So we're going to use this power rule throughout the rest of this class. A weird one falls in number 2. So number 2 says, what is the derivative of y equals x? Well, we're going to see this one a lot, so let's pay attention to it. When you see x, hopefully y'all remember that x is the same thing as x to the first power. So when you find the derivative of this, you take the 1, bring it to the front, leave the x alone, and when you subtract 1 from the power, that gives you 0. And what you should remember from algebra is that when you have something raised to the 0 power, that is going to also be 1. So in this case, the derivative of x just ends up being the number 1. So how can we relate this to something we're going to see a lot later on? A nice little shortcut says that anytime you have a number multiplied by x, since the derivative of x always just goes to 1, your final derivative will just be the number in front of it. And we're going to see that in just a few minutes. Make sure you're also comfortable with negative exponents. So number 3 says y equals x to the negative third. When you find the derivative of this, so y prime will be, bring the negative 3 to the front, leave the x alone, and then subtract 1 from the power. Negative 3 minus 1 is negative 4, and that will be your derivative. This works for any negative power that you have, so we can do a second one. How about y equals x to the negative 1? So when you find the derivative y prime, you'll take the negative 1 and bring it to the front, leave the x alone, and then when you subtract 1 from the power, you get negative 2. Now, normally we will not write this 1 right here, so I'll go ahead and clean this up. This would be negative x to the negative second power. We'll usually just drop our 1s off in the process. But there you go. That is the basic idea of the power rule. Now, we're going to see this rule in a bunch of different variations. It also combines to form other rules in the next couple of videos. So we're going to make sure we get this rule down pat in this video. All right, little reminder about something from algebra, because we're going to need this in the next slide. If you recall from algebra, you learned how to convert radical notation into exponential notation by learning a conversion. So a conversion you probably remember is the following. When you have the nth root of x to the m, this is the same thing as x raised to the m divided by n. So you take the power of x on the inside and you divide it by the root, and that forms your new exponent. This rule will be very vital because we don't take derivatives of roots very easily. It's easier to do things with exponents. So for example, if you have the square root of x and the cube root of x to the fourth, let's write these in exponential form. So looking at the square root of x first, if you'll notice, you remember that when you have a radical and there's no number written there, it's understood to be a second root or a square root. And then the understood power of x on the inside is 1. So when you take those two numbers and put them in the form as my conversion up here, this becomes x to the 1/2 power. So that is what the square root of x is. Do this for any number. So if you had the cube root of x to the fourth, you would bring down your x. Once again, using your conversion, the number on the inside is your top number, and the root is your bottom number. So the cube root of x to the fourth becomes x to the 4/3 power. And we're going to need that conversion here in just a minute. The other conversion that we might need periodically is how do you deal with negative exponents? So if you recall, anytime you have a negative exponent in your problem, you can make that positive by putting it on the opposite side of the fraction or flipping it over. So remember that when you have something like x to the negative m, you can rewrite this as 1 divided by x raised to the positive m power. Now, this also works a different direction as we're going to see down here, but let's go over both examples. I would like you to write x to the negative fourth and 3 over x to the negative 2 with positive exponents. So x to the negative 4 actually matches the rule right here. If you have x to a negative power, you can write that as 1 over x to its positive power. So that would be 1 over x to the 4th power. This also works when you have a negative exponent in the bottom. This one's a little bit more common that we're going to see. When you have a negative exponent in the bottom, you can bring that entire x to the top, and you can rewrite this as 3 times x to the positive 2. So if you want to make a power positive, you just need to move it to the opposite side of the fraction. All right, so let me show you a couple examples where this might be useful. So example number 7, find dy dx if y is equal to the cube root of x. All right, so we don't know a rule to take the derivative of radicals as they sit. So we will have to convert this into its exponential form. So what I'm going to do is know that the power on the, root on the outside is 3, and the understood power on the inside is 1. So if I were to rewrite this using that same conversion from the last slide, this would be x to the 1 divided by 3 power. Now, this is in the form that we can do the power rule for. So I'm going to take y equals this, and we're going to find dy dx, which remember, that's just Leibniz notation that represents take a derivative. So I'm going to bring the power to the front, which is 1/3. Leave the x alone, and you do have to be a little bit comfortable with fractions going forward. So if you take 1/3 and subtract the number 1 from that, that would be negative 2/3. And this would be your derivative. Now, one thing you can go ahead and practice while we're here is that if you want to put this back into positive exponential form, you can put that negative power on the bottom, and we can write this as 1/3 x to the positive 2/3 power. For now, it doesn't really matter, but it's a good thing to go ahead and practice if you'd like along the way. Now, number 8, the derivative we probably could have done here a few minutes ago, but we wanted to make sure y'all are comfortable rewriting this. So if y is x to the 0.4, find dy dx. Now, this is already in the form that we can take the derivative of. So I'm going to take my power and bring it to the front. So that would be 0.4, leave the x alone. And if you subtract 1 from the power, and you can use your calculator to help you here, 0.4 minus 1 is negative 0.6. And for right now, if you want to type that in your homework, it will give you credit. But just for later on, if you need to put this as a positive exponent, I would leave the 0.4 on top, move the negative x to the bottom, and make it x to the positive 0.6. All right, so a couple other rules here. I'm kind of mentioned this a few minutes ago, but we haven't actually defined it yet. So let's do that here. So probably the nicest, or one of the nicest rules that we cover in derivatives is the constant rule, because it's just one rule you have to memorize. If you take the derivative of any constant function, your answer will always be 0. It doesn't matter how big or how small this number is, it always goes to 0. So the derivative of every constant is 0. For example, if y is equal to the number 8, and you want to find the derivative of this function, dy dx will equal 0. And you don't have to do any work involved. This will happen for every constant that you have to work. All right, now where that comes into play, and you got to be careful because this next rule is similar yet different. If you have a constant being multiplied by something, it works a little bit differently. So these do not always go to 0, so don't assume that. What this rule says is that if you have the derivative of a constant times a function, all you have to do, so we have constant times a function, you will leave the constant alone, but you still have to take the derivative of the function like you normally would. So that's probably using the power rule here. And then when you're done taking the derivative, you will multiply that derivative by the constant that you left alone. So let me show you how this works. Number 10, I want you to find dy dx if y is equal to 8x squared. So as you can see, we've talked about how to find the derivative of x squared. We can do our power rule there. The new thing in this problem is this 8. So officially, here's how we'll work this problem. You're going to find dy dx is equal to the constant in the front, you just leave alone. So I'll leave the 8 there. The derivative of x squared, you can use the power rule for. So you would bring the 2 to the front, you would leave the x alone, and you would subtract 1 from the power to give you 2x to the first. And then from here, you would multiply these two things together, and that would give you 16x. And that is your final answer. Now, as we go through more and more of these in this class, I'm not going to always show this step every time, so I do want to kind of show you what else you can do. So let me rewrite the problem over here. Y equals 8x squared. One thing you could do if you're comfortable, if not, you can go back to this rule, is that when you find the derivative of a number times a function, If you're comfortable doing the multiplication in step one, you can do it this way. If I take the 2 and bring it to the front like you would with a normal power rule, go ahead and multiply those two numbers together and you're fine. So 2 times 8 is going to be 16, and then you can subtract 1 from the power, which gives you 16x to the first. But like I said, the more and more we do of these, I do hope that you're comfortable doing that second way because it will make things go quicker. Not saying this is wrong, but it can add up steps you have to do if you break them apart every single time. All right, so now that we've kind of learned pretty much almost all the rules in this section, let's do a few more derivatives to get you comfortable. So numbers 11 through 14, I want you to find the derivative of each of these functions. So beginning with number 11, and I'm just going to use y prime again for this. So y prime will be, so negative 5 times x cubed. I'm going to take the power of 3 and bring it to the front. 3 times negative 5 is negative 15. X, and then if you subtract 1 from the power, this gives you 2. So y prime is going to equal negative 15x squared. Number 12, we have a slight issue here because you cannot take the derivative as this is. So if y is written in the form 7 over x to the 5th, then you cannot take the derivative. I know it looks tempting, but with a fraction, this doesn't work. The power rule only works if x is on the top of your fraction. So if I bring this x to the top, this is why we reviewed rewriting stuff, you're going to have 7 times x to the negative 5th power. Then from here, you can apply your power rule. So y prime would be, bring the negative 5 to the front. Negative 5 times 7 is negative 35x. And if you subtract 1 from the power, it makes this a negative 6. And like I said, for right now, you can leave it just like that. Or if you're practicing rewriting, this is the same thing as negative 35 over x to the 6 if I put it back into positive exponential form. Here's that same issue we saw earlier. We don't know how to take derivatives of radicals, so you cannot leave it this way but when you do your power rule. So what I need to do here is the 2 is fine. I need to rewrite the square root of x to the 7th in an exponential form. So if I bring over the x, remember, you take the power of x, which is 7, and you divide it by the root, which right now is understood to be 2 if there's not a number written there. Now we can do our power rule. So y prime is going to equal, I'm going to take the 7/2 and multiply it by 2. So 7/2 times 2 would be 14 over 2 x. And if you subtract 1 from the power, 7/2 minus 1 is going to give you 5/2. Now, one thing to be aware of on these fractions is that sometimes the numbers in the front will simplify. As you can see, 14 divided by 2 does give us 7. So you have 7x to the 5/2 power, and that will be your derivative. Number 14, just be, once again, I'm trying to mix in everything you might see. Just be comfortable with negative fractions as well. So this one we don't have to actually rewrite because it's already in the form that we can take the derivative of. So if I find y prime here, I would take the negative 3/5 and bring it to the front. X, if you subtract 1 from the power, negative 3/5 minus 1 is going to give you negative 8/5. And like I said again, I'm okay for right now if you leave it just like that. Or a little bit later on in this class, we will have to rewrite it as negative 3 over 5. And if I move that x to the bottom, it becomes a positive exponent of 8/5. Very good. So this is some more combinations of the power rule. All we did was mix in some extra constants for you to deal with. All right, and finally, the last rule for this video is not really a big rule, but it's one thing just to be aware of because it's going to be a little different in the next video. This is called the sum and difference rule. And this is where we're going to start seeing combination derivatives going forward. Now, this one is a little easier than the ones in the next video. So let's just focus on this one for right now. If you are taking the derivative of either the sum or difference of functions. So remember, if you don't recall, sum means addition and difference means subtraction. If your two functions are either being added together or subtracted from one another, that says we can take the derivative of everything individually. So for notation purposes, if you want to write this down, if you want to take the derivative of f of x plus g of x, you will take the derivative of f, the derivative of g separately, and then you will re-add those derivatives together. Same thing with subtraction. If the two functions are being subtracted, you will take the derivative of f, you will then take the derivative of g, and then subtract those two derivatives. Now you may be thinking, what about multiplication and division? That's the next video. Those rules are a little bit more complicated. We will get into that in the next one. For now, addition and subtraction, just take the derivatives individually. All right, so here's a good example, or a couple examples. I want you to find the derivative of the following two functions. Number 15 overall. We've done a lot of problems because the shortcuts saving us some time. Number 15 is y equals 5x squared minus 11x plus 4. So combining everything we've learned so far today, if you want to find the derivative of this function, they're all being added or subtracted, so you can do each one individually. So starting with 5x squared, I'm going to bring the 2 to the front. So 2 times 5 is 10. And if I subtract 1 from the power, it's just 1. Earlier, we talked about that the derivative of x is just 1. So if you just see an x sitting there, it goes to 1. And 1 times a minus 11 is still minus 11. 4 is a constant, and as we learned a few minutes ago, the derivative of every constant is 0. So I took the derivative of all three terms in order, and I'm going to box in my final answer. That's all there is to it. So make sure you take your time through them and find each derivative. The only downfall is something like number 16 might pop up where you're going to have to do some rewriting. So I see y equals the 7th root of x plus 6 over x squared plus 2/3 times x. Now, these first two terms are the issue because I can't take the derivative of those as they sit. So I need to rewrite those. The 7th root of x, so since my understood power is 1, this would be x to the 1/7 power plus, I can't have this x on the bottom, so I'm going to bring it to the top and make it 6x to the negative 2. Now, 2/3 times x is something we can take the derivative of, so I'm not even going to mess with that one right now. Now that I've rewritten all my terms, I can now go through and take the derivative of each one individually. So y prime will equal, first power rule, I'm going to bring the 1/7 to the front, leave the x alone, subtract 1 from the power, 1/7 minus 1 is negative 6/7. Move to the next one. Negative 2 times 6 is negative 12. Subtract 1 from the power, and that's negative 3. And just like the minus 11x in number 15, when you have a number being multiplied by x, remember the derivative of x just goes to 1, so your derivative here would just end up being 2/3, because 2/3 times 1 is just 2/3. And very good. So make sure that if it's not in the right form for you to use the power rule, you rewrite your terms before you do that. All right, tangent lines. We did a tangent line example in the last video, but we did it using the long technique. So now that we've learned a shortcut, we can do tangent lines a little bit more quickly. So recall from the last video that to write the equation of a tangent to the graph of a function, you must have a point and the slope of the tangent line. So let's remind ourselves how we will work problems like this. Number 17 says, find the equation of the line tangent to the graph of y equals x squared minus 2x at the point x equals 3. Now, the first issue I notice is that it says we need a point, but I only gave you the x value here. So if you want to find the y value, you need to plug 3 into the original function. So that would be 3 squared minus 2 times 3, which is 9 minus 6, which actually also ends up being 3. So since our x is 3 and our y is 3, the point we're going to use is 3, 3. The next thing you have to find is the slope. So from the last video, to find the slope of a tangent line, step number 1, you have to find the derivative of your function, which is going to be y prime. Now that we know the power rule, we can apply that. The derivative of x squared would be 2x. Since the derivative of x goes to 1, that whole derivative goes to minus 2. You are then going to take your same x value, and now you're going to plug it into the derivative to find the slope. So the slope would end up being 2 times 3 minus 2, which is 6 minus 2, which is 4. Now that we have a slope and we have the point, we can write the equation of our line using the point slope formula. So from the last video, that is y minus y1 equals m times x minus x1. If I plug all my values in, well, the y value that I found over here was 3. The slope that I found on the left was 4. And the x value that they gave me was 3. Multiply that 4 through. So y minus 3 equals 4x minus 12. And then if you add 3 to both sides, you will have your final answer. Y is going to be 4x minus 9. And that is how you find the equation of a tangent line. And like I said, you can go back to the last video if you need a recap on that. But this is the technique we can use now that we know a shortcut. So that you have a second one in this video and a second one that you can put in your notes, let's do number 18 as well. Number 18 says, find the equation of the line tangent to the graph of y equals 1 over x cubed at x equals 2. All right, same issue here. We need a point, and I only gave you the x value. So first thing I'm doing is plugging this into here to get my y. So y would be 1 over 2 cubed, which is 1 over 8. So the point that I'm going to use here is 2 comma 1/8. I need to find my derivative, but I can't take the derivative of 1 over x cubed as it sits. I need to rewrite this. So first thing I'm going to do is bring that x cubed to the top and rewrite this as 1 times x to the negative 3. If I now take my power rule, y prime is going to be negative 3 times 1, which is negative 3, x, subtract 1 from the power, and is negative 4. Now here's where I warned you earlier. We stopped a lot earlier at this point, but since we're going to have to plug this x value into the derivative, you need to simplify this or clean it up. So I'm going to bring that negative 4 power back to the bottom. Oops, sorry. And I'm going to write it as the following. Leave the negative 3 on top, and on the bottom, this becomes x to the positive 4th power. I can now take this 2, and I'm now going to substitute it into my derivative to find the slope of the tangent line. So m is going to be negative 3 over 2 to the 4th, and if you use your calculator, you should be able to see that 2 to the 4th is 16. Now that we have a point and we have a slope, we can use our same point slope formula at the very top of the screen. I'll box it in blue to write the equation of this tangent line. So this would be y minus my y value, which is 1/8, equals the slope we just found, which is -3/16, times x minus my x value, which is 2. If I multiply the -3/16 to both terms, this is y minus 1/8 equals -3/16x. Let's see, a negative times a negative is a positive. -3 times, let's see, that's 6/16. Now 6/16 does simplify, so that is y minus 1/8 equals -3/16x plus 3/8. Just divide both of those by 2. I am then going to add 1/8 to both sides. So when I do that, you get y equals the -3/16x. And when you add 3/8 and 1/8, I'll do that over here on the right, that becomes 4/8. And since both of those numbers are divisible by 4, this actually becomes 1/2. So your final tangent line here for this problem number 18 would be y equals -3/16x plus 1/2. All right, now that we've kind of gone through some tangent line ideas, we have learned over the last two sections that the derivative of a function helps us find the slope of a tangent line. In algebra, if you remember, y'all talked about horizontal lines at some point. The one thing you need to remember about that is that every horizontal line has a slope of 0. So what we can say is that in the graph below, at x equals 0 and at x equals 4, we can say that the derivative is actually equal to 0. Because what ends up happening is that when you get to these two particular points, we talked about what tangent lines were. The tangent lines at these 2 points end up being horizontal. So all in all, while the graph is beautiful, this is the big thing down here at the bottom in this asterisk. You're going to have to be able to find these locations without always having the graph in front of you. So to find the location, and when I say location, I mean the x value. To find the location of a horizontal tangent on a graph, what you will have to do is you will take the first derivative of the function. You're not going to plug anything into it. Instead, you're going to set it equal to 0, and you have to solve the equation. That may involve some simple solving. It may involve some factoring. It all depends on what the original problem says. But to find where a horizontal tangent occurs, you will set the derivative equal to 0. So let's do an example of that. Number 19. I want you to find every point on the graph of y equals x cubed minus 2 at which the tangent line is horizontal. So when you see this word tangent line and horizontal, that is telling you to do two things. Number one, find the derivative of your function. So y prime is going to be, so doing my power rule here, 3 goes to the front, the derivative of x cubed becomes 3x squared. And since minus 2 is a constant, that derivative goes to 0. So just ignore it. Take the derivative and set it equal to 0. And your job is to solve for x here. If I divide both sides by 3, you will get x squared equals 0. And then if you take the square root of both sides, you will end up getting x is 0. So this is the only x value that makes a tangent line be horizontal. Now in the instructions, it says find the point. Since this is only the x value, you also need the y value. So you can get your calculator out if you'd like. You're going to plug 0 into the original function to get y. So that would be 0 cubed minus 2, which comes out to be -2. I believe on the homework, you're going to have to write this as an ordered pair. So remember, xy is your ordered pair. We found x to be 0, and we found y to be -2. So your only answer to this problem, the only point that gives you a horizontal tangent, is the point 0, -2. All right, and like I always do, I always end the section with a word problem. So this is our last problem for section 1.5. Number 20 says the temperature T of a person during a certain illness is given by the following function, where T is the temperature in degrees Fahrenheit at time T in days. So capital T of T is -0.1 T squared plus 1.2 T plus 98.6. I want to answer these three questions to end this section. So let's read through part A. It says, find the rate of change of the person's temperature with respect to time. So the key word here is rate of change. Rate of change, as we talked about in the last video, we represent by taking a derivative. So when it says find the rate of change, it is asking you to find the derivative of this function. So I'm going to find t prime of t by doing my power rule. I'm going to bring the 2 to the front to make that -0.2t, because when you subtract 1 from the power, it's t to the first. The derivative of t, just like x, is just 1. So this just becomes plus 1.2. And the derivative of 98.6 is just 0. So that is the answer to part A. This is your rate of change. Part B says, find the temperature of this person after 1.5 days. Now, it doesn't say anything about rates of change here. So I'm going to take this 1.5, and I'm not plugging it into the derivative I just found. I'm going to plug it into my temperature function given up here. So I want to find T of 1.5. This would equal -0.1 times 1.5 squared plus 1.2 times 1.5 plus 98.6. And pardon me, I said you can pause the video if you'd like to. I'm going to type all this into my calculator that I'm doing. You might be able to see me on the screen. If not, I'm doing it behind the scenes right now. At least I hope I am. There we go. So our temperature is 100.175 degrees. So according to this, after 1.5 days of being sick, your temperature should be about a little over 100 degrees. So obviously you're still sick at this point. The question becomes, this is where the derivative and the calculus part plays a role. I want you to, find the rate of change at t equals 1.5. Okay, so right there. It says find the rate of change at this 1.5. Remember, rate of change is derivative. So I'm going to take this 1.5 and I'm going to plug it into the derivative that I found on part A. I'll come back to the second part in a second. So we're going to take t prime and we're going to plug 1.5 into that. So this is -0.2 times 1.5 plus 1.2. Knock that, or type up my calculator really quick. And you get an answer of 0.9 degrees Fahrenheit. So that is the answer that you get. Now that's a really, really small temperature. Because remember, this is not your actual temperature. You would be dead if you were at 0.9 degrees Fahrenheit. But what does this mean? Remember, this is a rate of change. So what this says is that after 1.5 days of being sick, your temperature is increasing. And the reason I say increasing is because it's a positive number. If it was negative, you'd be decreasing. So after 1.5 days of being sick, your temperature is increasing at a rate of 0.9 degrees Fahrenheit per day. And I know it's per day because at the very top it says T represents days. So based on this knowledge, it looks like after 1.5 days, you're actually going to end up having a higher temperature a little bit later. What you hope for is you want that rate of change to be negative here, because that means your temperature is going back down and you're starting to get better and feel better as well. So that ends section 1.5. So we went over how to take the derivative using power rule. We talked about constants and constant multiple rules, and we talked about the sum and difference rules. In the next video, we're going to move into what happens when things are multiplied and divided and how you take those derivatives.